So, in the last class we finished the proof of this very important theorem, and in a way a surprising theorem. It was long conjectured in cryptography and finally proved by Nissan Wigderson in 1988. So, the theorem showed that if you have a E explicit Boolean function that is average case hard, then accordingly you will also have a PRG with the non-trivial stretch. Okay, so, hardness would allow you to stretch strings so that they look random to limited resource computation. And then we showed a very minor lower bound assuming the existence of a PRG. So, PRG implies lower bound implies PRG. What we will do next is we will see more applications of this concept of PRG in complexity theory. In particular, at the end of this topic or this section, you will see the complete proof of the first theorem that we started with in the course, which was if PIT is in P, identity testing, if it is in P, then it implies either Boolean circuit lower bounds or arithmetic circuit lower bounds. So, there was a lemma complexity theorem there which we did not complete the proof. We will complete it now using PRGs. So, we will now see more impressive applications of PRG. In complexity theory. So, first is using the hardness of permanent, you can de-randomize BPP. So, first is partial de-randomization from worst case hardness of permanent. But the theorem statement will look more impressive than this. So, actually in the theorem what we will say is it is a theorem by Impagliazzo and Wigderson. From 1998. So, it says that if BPP is not equal to EXP, which is a very reasonable hypothesis, everybody conjectures this, that using randomized polynomial time algorithms you cannot solve all the problems that are computable in exponential time. So, if this statement is true, notice that this statement does not have any circuits in it. So, if this statement is true, this already will imply a partial de-randomization. What will be shown is for all L problems L in BPP, there exists a sub-exponential time algorithm A solving L on average. By which we will mean here, we will mean that on almost all the inputs A can solve L, and it is sub-exponential time deterministic algorithm. Okay, so this is a partial de-randomization of BPP, and mathematically we will define this average as for infinitely many n's the probability over n bit inputs x of A solving L. Okay, this is high. So there are two things. One is that it may not work for all n, but it will work for infinitely many n's. Second is, even when it works for an n, it works for a large majority of the inputs in 0, 1 to the n. It may not work for all 0, 1 to the n strings. So let us prove this. So here we will break into two cases. First is whether x is not in P/poly, other is it is in P/poly. So when it is not in P/poly, then that's kind of the easier case. Then there exists a problem in EXP with worst case hardness large, right. So if EXP is not in P/poly, it means that there is a problem which is solvable in exponential time, but doesn't have polynomial size circuits. So in other words, worst case hardness is more than n to the omega 1. This little omega 1 means function that is growing, a growing function, okay, it diverges to infinity. So later we will see how to amplify this. To get f prime in EXP, another problem which is average case hard. This is called worst case hardness to average case hardness. This amplification procedure we will see in the next chapter. We will see it in great detail. It will be using error correcting codes. So let us assume all that for now and finish this part of the proof. So you have from f you have f prime, and then from f prime you have a PRG. So Nizan-Wigderson theorem gives then BPP in super poly hardness average case means sub-exponential time de-randomization. So that is done. That was kind of the easy case when EXP is not in P/poly itself, that gives you hardness, and hardness gives you de-randomization. Now what happens when EXP is in P/poly, right? Then there is no hardness. What do you do then? So then EXP is equal to PH. So recall that we had shown when we were doing initial lectures on identity testing that there were these sequence of results. EXP in P/poly meant that EXP is in MA, MA is known to be in the polynomial hierarchy, which is known to be in EXP. We had this sequence, right? And from this sequence it means that these three classes are equal. So, you have EXP equal to MA equal to PH. So, recall that. So, we immediately deduce that EXP is equals actually polynomial hierarchy, and moreover polynomial hierarchy is in p raised to permanent. This also you recall, which is again in EXP. So, this means that actually all these four classes are equal. So, EXP in particular is p raised to permanent. So, this by the way is called Toda's theorem, polynomial hierarchy in p raised to permanent, and permanent obviously is solvable in exponential time. So, you get all these four classes equal, in particular focus on EXP equal to p raised to permanent. Now, you have assumed that BPP is not in EXP in the hypothesis, right. So, which means that permanent is not in BPP. And you know that BPP is in P/poly. So, we do have some hardness. In particular, if you look at permanent, this does not have poly-size circuits, it requires super poly circuits. So, it makes sense to use permanent in Nissan-Wigderson map and get a PRG. So, permanent is hard, and we will use it to define this potential PRG map G. So, NWI permanent, where I is your Nissan-Wigderson design, permanent is the hard function. It should stretch 0 1 to the L to N. In the previous lecture note we used M, but here we will continue to use N, just appropriately rename the design parameters with a super poly stretch. That is the idea. What is not clear is how to use this NW map. Permanent is hard, but it is not really average case hard. So, we have to see how to go around the conditions required for Nissan-Wigderson theorem. That is what we will do next. Let us look at it in detail, this implementation. So, for L in BPP, if B x comma r is the randomized algorithm, solving L, then we define a kind of de-randomized algorithm using G. So, then we define de-randomized A as so that definition is simply, as you can guess, as you have seen before, B will use the output of or the image of G as a pseudo random string. So, A on X is just the majority vote. Okay, so this is just the majority of all these values of B x comma G image over all the image elements of G. So that reduces the random string from requirement of N to requirement of L, and you can think of this as a de-randomization, because now you can do this in 2 raised to L time. So that is the new algorithm A. So now suppose the theorem is wrong. Then for all except finitely many what you will get is that probability over the input x's Ex equal to Lx So this algorithm A that we have defined, suppose this does not satisfy the theorem statement. So which means that only finitely many n's this inequality holds, and for the rest infinite minus finite. For those n's, what is happening is that A and L, their values on x, they match with a very low probability, right. This is the negation of the theorem statement. So for all except finitely many n's, probability of Ax equal to Lx is less than 1 minus 1 over n, that is the negation. So what will this give you? So this implies that probability over the x's that majority of B x comma G U L is different from the majority of B x comma U N So majority of B x comma G U L, that is A on x, and the other thing majority of B x comma U N, this is really L of x, right. The whether x is in L or not, that is really this majority vote when you look at n bit random strings being used by B, then the majority answer is of course correct by assumption, because L is in BPP. So these two are different with probability greater than 1 by n. So you can see that B is kind of discriminator. It is able to distinguish between the image of G and the uniform distribution. Okay. So you can already feel that this should lead to some kind of a contradiction to PRG definition or NW definition. So we can fix x to be these strings, one of these strings where B is a distinguisher or discriminator, such that the circuit family Dn defined to be B with this string Sn fixed, x fixed to Sn, and the second argument we keep free. This can be G image or this can be UN. So this circuit So, this can distinguish GUL from UN very well. Right, DN are these algorithms and hence circuits. You can also see them as circuits. They are able to distinguish the image of G from the uniform distribution. In fact, DN is constructible by a randomized polytime algorithm. Right, because DN is essentially B, which was a given algorithm, explicit algorithm. You only have to fix SN string, but you can see above that this string you can just randomly pick, right, because the probability of being a distinguisher is pretty high. It is more than 1 by n, so you can easily pick it. So, DN is a easy circuit, also explicitly constructible. So, next question is what can you do with this distinguisher? So, for this you go back to the NW map properties we saw last time. So, recall the properties of NWI permanent, which we are calling G here. So, deduce that there exists a randomized polytime algorithm T that can learn permanent. So, this is essentially the idea of bit predictor that we saw while analyzing the NW map. Okay. Any algorithm like in this case DN, any circuit family that is able to distinguish NW from the uniform distribution will actually give a bit predictor, and the bit predictor in this case would mean that it will give you permanent computation. So, this algorithm we are calling T, this you get from the bit prediction basically. So, you have learnt permanent, and which means that given oracle access to permanent, oracle access to permanent T runs, let us say permanent on n by n matrix, big N by big N matrix. So, T runs in polynomial in that much time, and produces a circuit. Size circuit computing permanent. So, this learner for the permanent is there, but it requires oracle access to permanent, right. It basically requires it to compute permanent on smaller instances. So, how will you get the oracle, or how do you eliminate the oracle? you eliminate it by using the identity that permanent satisfies. So, eliminate the oracle access by using the self reducibility. By using self reducibility of permanent, which means what? Which is basically this identity, permanent on a matrix equals sum over smaller permanents. Over all I. So, that is how it does not matter whether you have the oracle or not, because once you have this algorithm T that reduces permanent to smaller permanent, it will be enough. Okay. So, basically you can build now, T can build using these circuits for permanent n minus 1, T can build circuit for permanent n, and the size bound will be small because T is after all a randomized polynomial time algorithm. So, the size bound cannot be bigger than the time complexity. So, T builds permanent 1, permanent 2, dot dot permanent n recursively. Giving small circuits. Because of its time complexity that we know. So, this is how you will learn permanent. This actually goes into the depths of this NW map and the bit prediction that we learnt in the last class. So, using this distinguisher Dn, you get algorithm T. Using T you get circuits for permanent, and circuits for permanent would give you, in fact these are actually algorithms to compute permanent, right. So, you get that P raised to permanent has randomized polynomial time algorithm. Any problem that you can solve using permanent, you can also solve using T in randomized polynomial time, which means that P raised to permanent is in BPP, which is a contradiction. Why is it a contradiction? Well, because in the very beginning you had assumed that permanent is not in, P raised to permanent is not in BPP, right. That was the hypothesis we started with. So, that contradiction happens. So, this contradiction shows that our assumption that B can discriminate was wrong. B cannot discriminate G from uniform distribution, and which means that A is the correct algorithm. So, AX is mostly correct. Okay, so this finishes the proof. Again, the proof may look tricky, but it is really just using the NW map and the way a distinguisher can be used to predict bits for NW map, which in this case meant that you are solving permanent. Okay, that was the contradiction. So, if BPP is not equal to X, which we all believe, then any randomized polynomial time algorithm can be de-randomized in subexponential time with this infinitely often solution in the average case. And we can also add infinitely often here and infinitely often. Okay, so it's infinitely often n, and for each such n average case de-randomization and subexponential time. So, that is one application, it is very non-trivial. Second thing we will do, second application is the theorem that we could not prove before. Now, let us move to the earlier unproved theorem. So, this is by Impagliazzo, Carbonates and Wigderson. It says that if NEXP is in P/poly, which we do not believe, by the way. If NEXP is in P/poly, then NEXP and EXP are same. So, this is a theorem statement where there is no mention of randomization or PRGs, right. But believe it or not, we will prove it using PRGs, all these advanced methods that we have invented. Whose statement has no PRG. So, the proof here is again it will be by contradiction. So, let us assume that exp is not equal to NEXP. Assume x which is contained in NEXP is smaller and which is in P/poly. So, there is some opportunity here for using this Nissan-Wigderson map and bit predictor and de-randomization connection, because you know that there is a problem in exp that is not in P/poly. So, it is worst case hard. So, the idea is there exists a problem in NEXP which is not in exp. Yeah, it will actually be already because of NEXP different from exp. So, since we are assuming NEXP different from exp, there is a problem L in NEXP which is not in exp. So, it is harder than exponential time, which can be used. Actually, this since NEXP is in P/poly, it also means that exp is in P/poly. Maybe I should write that here. So, there is no circuit hardness neither for NEXP nor for exp, but since we are assuming NEXP different from exp, there is hardness of a NEXP problem L with respect to exponential time computation, and we will use that. So, which can be used to get a hard function Now, by hardness versus PRG connection, we get a poly stretch the containment of exp in MA. Right, remember that exp when you assume NEXP in P/poly, like we recalled before, you immediately get that exp and MA are in fact equal. And since exp and MA are equal, MA has some, MA obviously is this Merlin-Arthur protocol. So, Arthur has random bits, so that de-randomizes Arthur. In this result, in this MA protocol for exp. Okay, so Arthur will be made more or less, it will be I mean the random bits which Arthur was using in this protocol, MA protocol, those bits will be eliminated. That is the goal. And then it will be like exp is in NP, okay, that kind of a result we want to reach. And then ultimately, finally contradict the time hierarchy. Yeah, finally we will contradict the, let me not say which hierarchy, we will contradict some hierarchy. That is a very rough goal. Okay, so use L which is not in exp to de-randomize the Merlin-Arthur protocol for exp. So, let us see this in action now. So, pick L in NEXP. So, there exists a constant C and relation R. So, relation R x comma y testable in exponential time such that just the definition of L in NEXP basically. So, x is in L if and only if there exists a certificate which is exponentially long, certificate y, satisfying the relation. That is the obvious property of NEXP, that any problem there L, a yes string x will have a certificate which will be exponentially long. So, we are assuming it to be 2 raised to x raised to c, and the verifier R will also be exponential time, which we are assuming to be 2 raised to x to raised to 10 c time, right. This is just the setting or the notation. Now, the question is, this very long string y, what can you say about its circuit complexity? Is this a hard string? Is there a compact representation for y? So, what is the complexity of the certificate y? Now, this circuit complexity cannot be very small, because if it was small, then we could actually guess it faster, and then that would put L in exp. That cannot happen, right. So, this suggests strongly that Y has a large circuit complexity. So, it is actually encoding a Hart function. So, view Y as a truth table. So, think of Y, this exponentially long string, as a truth table of some function, and look at the circuit complexity of that Boolean function. So, for parameter D, let us define MD be the following machine. On input x in 0 1 to the n, so essentially we are asking the question whether this MD will be solving the question whether there is a small circuit whose truth table is Y. So, that is what this MD will be checking. So, enumerate circuits of size n raised to 100 D with n raised to C bit input. Y n raised to C, because length of Y is 2 raised to n to the C. So, we want to look at Y as a truth table of n raised to C bit input function, and it is a Boolean circuit, it outputs only one bit, right. So, for each such circuit C, let TTC be the truth table. Be the 2 raised to n raised to C bit What is a truth table? So, truth table is just evaluation of C on every possible input. There are 2 raised to n raised to C possible inputs. So, look at these evaluations as a single string, that is your TTC. So, if there exists a C, with R x truth table C equal to 1, then output yes. Output 1. Okay. So, if there is essentially what this Turing machine MD is doing is that it is just looking at all circuits of some size n to the 100 D poly size circuits, and trying to see whether the truth table of such a circuit could certify X. If it does, it will say yes, otherwise it will say no. So, this is the Turing machine to test. basically it is searching y. But it is searching not all these y's. Y is a very long string, so that space will be doubly exponential. Instead of searching for all y's, it is searching y which are truth tables, special y's, as truth tables. If it finds, it says yes, otherwise no. What is the time complexity of this algorithm or this Turing machine? So MD runs in time just exponential in this n raised to 100d, because it has to look at all the circuits. So let us say time is n raised to 101d, and it has to run r also. So complexity of r was n raised to 10c. Right, this is the time complexity of the algorithm m sub d. So since L is not in EXP, MD cannot solve L. For any constant d, MD will not be able to solve L, which means that MD will not be able to find y. That is unable to find y. So which means that for all d, there exists an infinite sequence of inputs. Let me call it chi d, on which MD will reject, MD will say no or 0, but so input was x, and what it was searching is actually a certificate. So this is actually SI is in L. Basically a certificate y exists for this SI, but it is not of this small circuit truth table type. It is of a different type. Okay, its circuit complexity as a truth table is, the function is actually very complicated. It cannot be written as a circuit of size n raised to 100d. So remember this. Okay, there is an infinite sequence of inputs that are fooling MD. So for all x's in chi d, these are the hard inputs of L. So for all x, certificate y, for which Rxy is 1, is a truth table of a hard function. That cannot be computed, that is not in size n to the 100d. So it is a function certificate for these x's is a truth table of a function that requires circuit size more than n to the 100d, right. This is clear. So by this worst case hardness based PRG. Remember that worst case implies average case. This we will prove in the next chapter, and from that already we can invoke that theorem, and from that what you will get is these these hard functions which y encode, these hard functions can give you a super poly stretch PRG. We use y to get an L to the D PRG, which we call GD. Okay, so this hardness actually is giving us GD. And how did this hardness come about? Because we assumed NEXP different from EXP, and then we picked the problem L in NEXP, and based on that we have a super poly stretch. So remember this. Okay, this much we have from the hardness to PRG connection. What next? How do we get a contradiction? So recall that exp in P/poly implies that exp has MA protocol. So thus for any problem L prime in exp, Merlin proves that a string x prime is in L prime by sending a proof. And this short proof is verified by Arthur. Arthur verifies it by a randomized algorithm in n to the d steps. So n is the length of the input. Okay, so every problem L prime in exp, Merlin will send a proof basically to actually prove that x prime is in L prime. X prime is a yes string. Merlin will send a proof to Arthur, and then Arthur is a randomized verifier, so it will run an algorithm. Let us say time complexity is n to the d, n is the length of the input, supposedly yes string x prime. So idea here is Arthur could use this PRG GD. So Arthur can use GD to remove the random bits that he needs. So let x prime prime be a hard string, hard input. X prime prime length is n. So Arthur guesses y. Arthur guesses y such that this is 1 and uses y to design GD. Right. So, basically what is happening is Arthur can use a hard input xd, and then it is known that the certificate will be truth table of a hard function. So, that y Arthur can guess, and once guessed it is a truth table. So, it is a function, and using NW map construction GD is the PRG. So, now for Arthur GD reduces the random bits. From n to the d to n. Okay, so now fewer random bits are needed because thanks to this PRG. Okay, so what can you say about Arthur? As a verifier, what are the parameters? What is the time complexity, random bits? We have also introduced non-deterministic bits in Arthur, right? So, let us now collect all that information. So, Arthur needs n to the d and exponential in n to the 10c time. Why exponential in n to the 10c time? Well, that is again to compute r, right? And Arthur was already its complexity, his complexity was n to the d time. So, we keep that. So, Arthur is this much time algorithm, but it needs random and non-deterministic bits. So, random bits he needs n many, and x prime prime has to be guessed, that is another n bits, that is the advice needed. N advice bits, that is x prime prime, and there is a guess to be made which is y, 2 raised to n raised to c. Bit guess which is for y. Okay, so, these are the parameters. Advice means that somehow this x prime prime will be needed, that is n bits, random bits are n, which then can be stretched by GD. Time is 2 raised to n raised to 10c, and the non-deterministic bits are 2 raised to n raised to c. This is the parameter, and we will finish the proof next time.